Welcome to the deep dive. Today, we're skipping the usual noise and going right to the source.
We are, and our source today, it's excerpts from a quantum physics textbook.
Right. Now, that might sound a bit heavy, but think of it like getting the inside scoop on reality itself, the really fundamental level.
Exactly. And for you, the learner, listening in, our aim is to pull out the key stuff, the core ideas.
Yeah, we want those aha moments, you know. We're not trying to drown you in equations.
No, definitely not. It's about grasping the sheer strangeness and fascination of the quantum world quickly but properly.
So our mission today is basically exploring quantum mechanics 101. We'll look at probability huge in quantum and measurement, which is super weird.
And just why the universe at its smallest scale seems to ignore all the common sense rules we see around us.
Okay, let's dive in. Probability. In physics, it's not always straightforward, is it?
That's a really good place to start. The text points out there are really two main ways probability pops up. First, there's the classical kind. Uncertainty just because we don't know every little detail. Think like a pendulum.
You might not know the exact air friction or the tiny wobble in the pivot, that kind of thing.
Precisely.
Yeah.
Or the book uses the example of a thermos. Predicting its temperature drop involves loads of tiny unknown factors. But crucially,
You could know them in theory with enough work.
yeah, exactly. The textbook says you can often shrink that classical uncertainty, get better measurements, expand the system you're looking at. Like with climate modeling, you factor in more and more interactions.
Right. Makes sense. But then there's the quantum version.
Ah, yes. And that's, as you said, a whole different beast. Quantum uncertainty isn't about missing information.
It's inherent. Baked in.
That's what the source says. Woven into the fabric of reality itself. It means even if you had the most complete knowledge possible about a quantum system.
You still couldn't predict some things, for sure.
Exactly. Some measurement outcomes remain fundamentally probabilistic. The universe, at rock bottom, isn't perfectly predictable like, say, clockwork. There's inherent randomness.
Wow. Okay, that's radical. So measuring, say, an electron spin, the outcome isn't set in stone beforehand.
That's the core idea. And the book adds a couple of layers. One, we rarely know the exact state of our measuring device at the quantum level. Two, and this is key, the measurement itself disturbs the tiny system.
Ah, so you can't just peek without changing things.
You really can't. It leaves the atom, or whatever you're measuring, in an uncertain final state. What quantum mechanics does give us is the power to calculate the probabilities for each possible outcome.
But not always the definite outcome itself.
Not always. That inherent uncertainty is just there. It's fundamental.
Okay, probability is key. Got it. So how do we actually work with these quantum probabilities? The textbook brings up coin flips and dice. Seems a bit basic.
Hey, yeah, it's like going back to basics, but for a good reason. It's a
Yeah.
bridge. It reminds us how classical probability works. Flip a coin n times, event A happens in A times. The ratio in n gets closer and closer to the true probability, PA, the more you flip.
Right, the law of large numbers, sort of. Flips settle around 50-50.
Exactly. And if you have independent things like rolling two dice, the chance of getting, say, a specific number on both is just the individual probabilities multiplied together. PAB equals PA times PB.
Simple enough. But quantum isn't simple multiplication, is it?
No. This is where it takes that sharp turn. Quantum mechanics calculates probabilities in a unique way, using something called probability amplitudes.
Amplitudes. Okay, what's the deal with those?
This is where it gets really wild. Instead of a probability being just a number between 0 and 1 in quantum mechanics, we first calculate a complex number, the probability amplitude, let's call it A.
Complex number, like with imaginary parts?
Yep. And the actual probability is the modulus squared of that complex number, so P equals A2.
Okay. Why the extra step? Why complex numbers?
Because complex numbers have both a magnitude and a phase, like an angle. And when you combine possibilities in quantum mechanics, you add the amplitudes, not the probabilities. And because amplitudes have phases, they can interfere.
Interfere. Like waves.
Exactly like waves. This is where the famous two-slit experiment comes in. It's the perfect illustration.
Ah, the two-slit experiment always comes up. Explain how amplitudes make sense of it.
Okay, so imagine firing electrons, one by one, at a barrier with two slits. Behind it, there's a screen to detect where they land.
Classically, you'd expect two blobs on the screen right behind the slits, like firing paintballs.
You would. But with electrons, you get this pattern of stripes. Alternating bands where lots of electrons land and bands where almost none land. An interference pattern.
Even sending them one at a time. How?
That's the mystery. It suggests each electron somehow knows about both slits. Quantum mechanics explains this using amplitudes. The amplitude for an electron to reach point X on the screen is the sum of the amplitude for going through slit 1 plus the amplitude for going through slit 2. Let's call them A1x and A2x.
So AX, A1X plus A2X.
Right. And the probability is A by 2, which is A1x plus A2 by 2. When you expand that, you get A1 by 2 plus A2 by 2 plus an extra bit.
The interference term.
Yeah, exactly. It involves the phases of A1 and A2. This term IX equals 2x, P1x, P2x, where P1 and P2 are the probabilities through each slit individually, and Phi1, Phi2 are the phases.
And the cosine part makes it oscillate, creating the stripes.
Precisely. Where the phases line up, you get constructive interference, high probability. Where they're out of sync, you get destructive interference, low probability. It's the adding of complex amplitudes that does it.
So the wave-like pattern comes from the math of these amplitudes, but you're saying electrons aren't actually little waves.
Well, the textbook is careful here. It says that while the math looks exactly like wave interference, light does this too. We shouldn't necessarily conclude that particles are waves in the classical sense, especially in non-relativistic quantum mechanics.
So the math works like waves, but the underlying reality might be something else.
Something that requires this amplitude description. The interference arises from how these complex amplitudes add. It's a quantum phenomenon that can happen in ways not just tied to spatial movement, even if the two-slit experiment is the classic visual.
Okay, that's a lot to absorb. The math mimics waves, but don't call the particle a wave.
Got it. Now, the book then dives into quantum states and Dirac notation. Sounds formal.
It is a bit more formal, but Dirac notation, those funny brackets, kits and Brasparaf, is actually super elegant. It's a shorthand developed by physicist Paul Dirac.
Okay, what do they represent?
A ket, like psi, represents the complete quantum state of a system. All the information you can possibly have about it captured in this abstract vector.
And the Brachev. The bra, it's like, well, it's a function that acts on a kit. When you put them together, you get a complex number.
Ah, the probability amplitude we were just talking about.
Exactly. FR is the probability amplitude for finding the system in state phi, given it started in state phi. The probability itself is then phi. Dirac notation just makes manipulating these states and amplitudes much cleaner.
Makes sense. And superposition, the idea of being in multiple states at once, how does that fit?
It's fundamental to the structure. Since kets are like vectors, you can add them. If first O is a possible state and first is a possible state, then frf is also a possible state.
So the system can literally be in a combination of state 1 and state 2?
Yes, until you measure it anyway. Every amplitude in state 3 is just the sum of the corresponding amplitudes from states 1 and 2. You can also multiply states by complex numbers. And any state can be broken down into a sum of simpler basis states, like using XYZ coordinates for position.
Okay, like building blocks. The textbook uses electron spin as an example.
Yeah, spin is a great example because it's purely quantum, no real classical analog, and often has just a few basis states.
Like spin up and spin down?
Exactly. For a spin-half particle like an electron, if we look at spin along, say, this axis, there are two basis states, plus spin up and spin down. That's it. They form a complete set for spin along zig.
So any spin state is just a mix of those two?
A linear combination, yes.
Yeah.
Sabindia plus A plus plus, where A and a plus are complex amplitudes. The probability of measuring spin down is a 2 and spin up is a +2.
And if you measure spin along a different direction, say tilted at an angle?
Good question. Let's say the electron starts in the pure spin-up state along z, so +A. Now you measure along a new direction n, defined by that angle relative to z.
Okay.
Quantum mechanics allows us to calculate the probability of finding spin down along this new axis n.
Yeah.
The textbook gives the result. Sin 2.
Just lemma theta over 2. So the probability depends directly on the angle between the preparation axis, z, and the measurement axis, n.
Absolutely.
Yeah.
If pho is 0, measure along n's again. Sin 2, 0 is 0, 0 probability of getting spin down, which makes sense. It started spin up. If pho is 180 degrees, measuring along z, sin is 1, you're certain to get spin down. If suth is 90 degrees, sin 245 is 12, it's 50-50.
Fascinating. Okay, so we measure, we get a probabilistic outcome.
Yeah.
What happens to the state when we measure? The book talks about state collapse.
Right. This is another one of those really counterintuitive central ideas. The text points out that ideal measurements should be reproducible.
Meaning if I measure spin up and immediately measure again, I should still get spin up.
Exactly. But think about the state before the first measurement. It might have been a superposition, say a mix of spin up and spin down, plus A plus A.
Right.
If you measure and get, say, spin up, the system can't still be in that mixed state for the second measurement to reliably give spin up again.
Ah, so the measurement has to change the state.
That's the idea of collapse. The measurement forces the system out of its superposition, and into the specific state corresponding to the outcome you measured. If you measured spin up, the state becomes plus. It collapses from the sum ik err down to just the single state that corresponds to your result.
So measurement isn't passive observation, it's active intervention.
In the standard interpretation, yes, it fundamentally alters the system.
Okay. Then there's expectation values and the uncertainty principle. How do they connect?
Expectation value, usually written in Q for some observable Q, is basically the average outcome you'd expect if you did the same measurement on many identical systems all prepared in the same state.
A statistical average, given the probabilities.
Precisely. And variance, which measures the spread around that average, tells you how much uncertainty there is in a single measurement. A large variance means the outcomes are likely to be widely spread.
And the uncertainty principle fits in here.
It does. It puts a fundamental limit on the product of the uncertainties, specifically the standard deviations, for certain pairs of observables. The famous one is position x and momentum p.
Sex times SPUP has to be greater than or equal to something small.
Greater than or equal to h bar over 2, where h is the reduced Planck constant. It's a tiny number, but it's not zero.
Meaning you can't know both position and momentum perfectly precisely at the same time?
Never. The more precisely you pin down the position, smaller socks, the less precisely you can know the momentum. U must get bigger, and vice versa. It's not about bad measuring tools. It's fundamental.
And this relates back to waves somehow.
Yeah, the textbook connects it to the wave nature. To make a highly localized wave packet, precise position, you need to superimpose waves with a wide range of wavelengths, which correspond to a wide range of momenta. To get a precise momentum, a single wavelength, the wave has to be spread out over all space, uncertain position.
It all interconnects probability, amplitude, superposition, measurement, uncertainty.
It really does. And the textbook wraps up by revisiting the two-slit experiment, reinforcing that the whole interference pattern boils down to adding those probability amplitudes for the different paths. That's the quantum magic.
Completely different way of seeing the world.
Absolutely.
Yeah.
Our everyday intuition just doesn't prepare us for it.
Well, this has been quite the journey into quantum fundamentals. We've really dug into probabilities, central role, the weirdness of amplitudes and superposition, how measurement changes things, and these built-in uncertainties.
It really highlights how different the quantum realm operates compared to our macroscopic experience.
Exactly. So for you listening, here's something to chew on, building on what we've discussed. How might this deep fundamental uncertainty at the quantum level actually ripple up and influence the world we do see, even if it's usually hidden? What does it really mean for reality if chance isn't just about us not knowing enough, but is actually part of the universe's basic design?
Yeah, big questions. We definitely encourage you to look deeper into the source material if this sparked your interest.
Thanks for joining us for this deep dive into the quantum world.